It's my pleasure to introduce Ankur Mani. So Ankur Mani is a PhD student at MIT Media Lab, where he's working with Sandy Pentland, and he's also collaborating with Asuman Ozdaglar at Leeds CSAIL, and as well as Parag Pathak, Department of Economics. So he's doing some interesting work in the intersection of economics, social networks, game theory. And recently he was a recipient of this award from Yahoo, which was to encourage grad students to propose these key scientific challenges which would define next few years of research. So please welcome Ankur Mani.
Thank you, Ashish. Hi. So today I'll be talking about exchanges in social networks and how do stable societies emerge out of these exchanges, and what kind of subset of social networks along which the exchanges happen. So this is work in collaboration with my advisors Asuman Ozdaglar and Sandy Pentland. So the line of the talk will be such like this. We will first talk about why we study these phenomena. People have studied stable societies in markets all the time, why social networks. And then we talk about the contributions that bring in this work. Some related work, a snippet of the related work. Then we introduce my model of localized exchanges in social networks, talk about the existence result, the stability and the efficiency debate, and we want to see a myopic dynamics that actually converges to stable exchange networks. And we have some experimental results that we'd like to see, whether do people actually behave in a certain way that can result in a stable society or not. So first question, why study local exchanges in social networks, right? So the key observation is that most species, including early humans, didn't have too much of a cognitive capacity, also the resources to look over the whole society. They only looked around themselves. They had limited visibility and limited cognitive power. So all the decisions were myopic both in the space and time. So they didn't look very far ahead. Most of the interactions were limited to limited time interactions and also to people around them. Even now, it is very hard to imagine that a person from Nicaragua will sell rice for wood to another person in Zambia, for example. It's very hard to imagine these things happening. Then why do we have these centralized markets, right? And so we want to study local exchanges because of these things. But still, even in those societies, we saw that societies were stable. And there were some properties related to the increasing social surplus in these societies a long time, because of which, by evolution, they actually grew, right? So that's why we want to study local exchanges. The another important thing is that the whole field of behavioral economics, shown by, introduced by Danny Kahneman, who's the Nobel Prize winner in the behavioral economics, showed that humans normally have two kinds of minds, the habitual mind and the attentive mind. So most of the decisions we make in our daily lives are through the habitual mind. It's well programmed, it's very fast and very automated. It's kind of a response action we do. We see something, we act something, right? We don't make very long-term plans. On the other hand, the attentive mind is actually very slow and very, very calculative, right? Most of the decisions in the real life are not made by the attentive mind, even things like exchanges and other things. So we want to see that do people with only acting with habitual minds, how do societies converge to stable solutions or stable points when people actually act like this? So on the other hand, when you look at the whole economic exchange theory, the markets, what happens? They assume there is a market owner. Everyone comes to the market, brings his product, or wants to buy the product, for example. The market owner sets a price. People disclose the demands for each good, given the prices, and then market owner allocates goods. So the classic literature says that at equilibrium, the demand meets supply, and that's how the stability emerges in the markets, right? So, and the other important thing is that stability emerges, and the stable points are also Pareto efficient. This is the first welfare theorem. Pareto efficiency means that if one person can increase the profit by changing his or her strategy, someone will actually lose this way. So that is the notion of Pareto efficiency. So this is what the general equilibrium literature says. But the catch is it's all in the sense of markets. You need to have a market owner. You need to have a centralized market where everyone comes and does that. How often do we see these things, right? So that's why we study exchanges in networks. Now, okay, when we do all this, what are the applications? What are the other things we can do, right? So now we see the emergence of all the social networking websites and also lots of other devices that we have with people. We actually have a much better idea of social network between people. So, but still at the same time, what we do is that with the emergence of internet, we are still talking about centralized markets, right? There's a big Google website or a Bing website where people say that I want to advertise. I pay some money, I bid for positions, and I'm allocated some search results or something like that, right? So what we're talking about we can leverage the infrastructure we have right now for social networks and talk about distributed markets, right? And so what kind of products, what kind of mechanisms we can design for distributed markets. So understanding of this thing is going to be very, very critical for designing such markets, right? We can also design public policies to increase social welfare. There are some people working on network governance. They can benefit from this a lot. We can also support organizational reengineering, talking about if we know what kind of social structures are beneficial for the people, then we can design policies, taxation policies or subsidy policies, so that certain interactions in social network are subsidized, other interactions could be taxed. So in the different incentive structure will lead to different organizational structures without saying explicitly to people that whom you are supposed to interact with, right? Other applications include strategic marketing and epidemic control. So once we said that, let's see, what did we do? So there are four main contributions that we'll discuss in this work. Of course, we have a model. First of all, we need to have a model of bilateral exchanges in social networks. Now, the first question exists, okay, we know that there exists equilibrium in markets. Does there exist a similar result in the case of networks? So we have this result that says that, okay, there exists a stable exchange network. That was an important result, otherwise we can't go any further. So the second result discusses that in what scenarios will stable set of exchanges in a network will also be socially efficient, in the sense that it actually maximizes the sum total of utilities of the individuals in the social network. And so what are the constraints? So we'll see those constraints. Thirdly, we want to see that can people, do there exist very simple rules, very simple policies with limited information requirements as well as limited computing power that people will need to make decisions myopically, and still the society will converge to a stable outcome. So we will show you that there exists such natural myopic behavior, and we'll show you an example of that, right? Then lastly is that, okay, when we know that, okay, agents can actually do that, will people do that? So we did some experiments in the lab, and turns out actually people behave very similarly, and there are experimental results that show that, okay, people will actually converge. Right? Okay, so just to give a small idea of what the related work is, there is a huge line of work on markets, both in the sense of equilibrium for price and demand, but also in the sense of matching, say a bunch of men and bunch of women. You want to match them so that they will not prefer anyone else other than their partner. So there's a long line of work, and which has also been applied to other similar scenarios such as residency matching and other things. But the interesting part is that what is the line of work in networks that is related to what we are doing? There's work by sociologists, by economists, by computer scientists. The two main papers that are very related to us is one by Rachel Cranton and Deborah Meinhardt, and one by John Kleinberg and Eva Tardos. So what did Cranton and Meinhardt say? So they are the first ones to propose in economics the theory of buyer-seller networks. They said that there are a bunch of buyers, a bunch of sellers. instead of everyone coming to the market, they have links, and they can only perform exchanges along the links. And so they proposed, they tried to understand what social structures were more efficient, in the sense that you can have an allocation in this scenario, such that the people who value the good more will get the goods, as compared to people who value the good less. Right. So on the other hand, the Kleinberg and Tartos, they studied what are the balanced outcomes in this scenario. Balance is an important concept. What it says is that if two people are in a contract, or they are performing an exchange, and they both have outside options, then the incremental payoff they are making in the contract between them is same for both the people. So that is the notion of balance. So the balanced set of outcomes in such a network is a subset of the stable set of outcomes, right? And they propose an algorithm to get there. Our work is very little different from that. We do not focus just on balanced set of outcomes. We try to propose a scenario in which people are just performing exchanges, and what are the stable set of outcomes that can arise, not restricting to splitting of a pie that most of this literature talks about, but talking about, okay, if people are having different kinds of utilities, what set of stable outcomes will they converge to, and when they have, what kind of behaviors will actually lead to stable set of outcomes. Right, so let's quickly get to the meat of the work. Right. So first let's put the model here. Okay. First, let's study what social networks looks like. This is a simplified social network. I'm just showing a bipartite social network. But you can imagine links between people within the same group. You can imagine links between people on the top and links between people on the bottom. But let's consider that the top people are the farmers and the bottom people are the woodcutters. Right? So farmers, it's hard to imagine farmers exchanging rice for rice, but it's easy to imagine farmers exchanging rice for wood. And that's why we, as far as the analysis is concerned, we can restrict to bipartite networks like this. So we have the social network, and it's another important thing is to understand that when farmers exchange rice for wood, they would like to go to the person with whom they can get most wood for least rice, so that they are most advantageous. And if there are multiple people like that, it's good to just get to one person, so that you don't have, if there are different prices for different people, you would like to pick the maximum, the person who's giving you the best price. Right. So in this social network, there exists a subset of this social network along which the exchanges happen. Let me show you, for example, in this social network. So here we see that only 2 of the links remain. Right. The other links are not there because the exchanges are happening only along 2 links. So this is the subset of social network along which the exchanges. We call it the exchange network. Right. How does the game happen? So people are there. They have certain initial endowments, maybe amount of rice or amount of wood, and they have to pick a partner, and they have to pick the terms of exchange: how much rice to give and how much wood to get for the farmers, and the other way around for the woodcutters. Right. So they have to make these kinds of decisions. So we more formally, let's get to the game. So let me put this more formally. We have 2 goods, X and Y, could be rice and wood, right? And we have n actors. With each actor has exactly one kind of good, either rice or wood, right? And then each actor has continuous, convex, and locally non-sated preferences over bundles of goods. A bundle would be a vector, 2-dimensional vector, which first element will be amount of rice, and second element amount of goods. So a convex preference means that if there are 2 bundles that are preferred with respect to which have a higher utility along with respect to another bundle, then the convex combination of those 2 bundles will also have a higher utility as respect to this bundle. Right. So that's the notion of convexity, which is very, very important, and it's also present in the general equilibrium literature. And local non-satiation means that if there is a bundle, then within any neighborhood of that bundle, there exists another bundle that is preferred with respect to this bundle. So these are two properties required, convexity and local non-satiation. And when we know that the preferences are continuous, then we can actually translate these preferences to a function, the utility function. So now that utility function will be continuous, quasi-concave, and locally non-satiated, right? So we say pi is their utility function, right? Now there exists a social network, which is the edges between the farmers and the woodcutters, and all these edges have some capacity constraint, which says that the amount of goods they can exchange is upper bounded to a certain extent, right? It is not always very important, but in some cases it's the results are important. The results depend on these capacity constraints, right? And exchange between the two neighbors determines the amount of rice given and amount of wood received from the neighbors, right? So now we say, let's say what is the pure strategy in this game. So pure strategy, as I said in the diagram, is to pick a partner and pick the terms of exchange, right? So, and given all these, given a set of pure strategies for all the individuals in this network, there is what are the utilities people derive. So two people perform a trade if they both pick each other, as well as they both agree on the terms of exchange, right? So when this happens, then you can get a matching in this social network, and that matching is the exchange network. And the utility of the people is actually the difference in the utilities between the final endowment and the new endowment, if they are matched. So you know that they will get a positive utility only if they are matched. If they are not matched, the utility will be 0, or the payoff will be 0, which is the difference between the utilities of the final endowment and the initial endowment. Okay, and so now we know that the strategy profile also introduces a unique exchange network, which is the matching, which is induced. So two people are in an edge exists in the matching if the two people are, at the ends of the edge actually pick each other as their strategy, right? So given this, the game can be just represented by this social network and the set of possible strategy profiles, which is just checking, choosing the partner and then choosing the terms of exchange, right? And then we say it is true that for one particular exchange network there could be multiple strategies. I can, with the same person, I can choose multiple terms of exchange, and so one particular exchange network can be supported by multiple strategy profiles. And similarly, if they support the multiple strategy profiles, we will have similar possible payoffs for one particular exchange network too, right? So we have this is the model. Let's understand what is the concept of stability in this model. So in general, when you have a game, standard form game, you look at the Nash equilibria to see that that is one probable stable outcome, right? So Nash equilibria says that if one person deviates while all the other person maintain their strategy, then the person cannot be better off, right? So if the strategy profile demonstrates that property, then it is a Nash equilibria. But in this game, it is not important, because technically all strategy profiles are Nash equilibria, right? Because all changes in this game will happen when two people simultaneously change their strategy. So if I propose a trade to Ashish, and Ashish has some other strategy, and if he does not change his strategy to trade with me, then I cannot change in any way. So any strategy profile is a Nash equilibria there. So that's why we have the notion of pairwise stability. It was first introduced by Matthew Jackson. So what he said is that along with the Nash equilibria, you should also have this idea that when two people are present in the network, they cannot simultaneously change their strategies in order to be better, both simultaneously, or at least one should be better and the other should be doing as good as she is doing right now, right? So we can restrict these pairs to be just the pairs who have an edge in common, or the people who are neighbors in this network. So what it says is that no two neighbors can simultaneously change their strategies as to make a link between them by breaking other possible exchange relationships or the contracts, such that they both, or at least one of them, is better off and the second one is as good as what she was doing right now, right? So that was the concept of pairwise stability, and we introduced the model. So now the another question is that does there exist a strategy profile that is pairwise stable, right? So do stable exchange networks exist? That's the question. So the answer is yes. So this is one of the results, and so the theorem says that in this presented model of network exchange, every network exchange game that we introduced will have a stable strategy profile, and every network game will also have a stable exchange network that is induced by that stable strategy profile. So why is this non-trivial? So the problem is that when we do it in the sense of markets, we have that the strategy space is continuous over there. So all you have to choose is the demand with respect to the price, and here what is the strategy space is discontinuous. You also have to choose the partner. So you have to choose one of the partners among your neighbors. So the strategy space is discontinuous. It's a little difficult to show how the existence of equilibria using any of the fixed point theorems that you use in proving of the general equilibrium. Right. Secondly, say okay, if we do something like we do in the matching, how would you do? So in the matching scenario, like a weighted matching problem, what you do is you prove the existence through duality of the stability problem and the efficiency problem. Suppose the maximum weighted matching, you want to maximize the sum of weights of all the edges in the matching. The stability problem there is to say that what is the value that you can assign to each edge, such that the sum of the values across any edge is more than the weight of that edge. So it turns out that those two problems are duals of each other, and the maximum weight problem is actually when you remove the integer constraints, nothing happens because it demonstrates total unimodularity. So there the duality actually helps in proving this. So that is not present here because the utility functions that we are showing here are not linear, right? So for nonlinear utility problems, how do you show that? So that is the problem. So the proof is a little long, so I will just go through the proof concept, and we can, if you are interested, I can send you the paper and you can look into the paper and we can discuss more about it. So to show this, what we do is to just consider a game between one party or one set of people, like only the farmers. So what we say that okay, let the farmers bid on the payoff that they want if they end up doing an exchange with anyone else, right? So each farmer I say is a buyer, and I'll say woodcutters as sellers. So that's to make sure that. So each buyer bids PI, which is the payoff that they want to obtain in the exchange, right? So this is the strategy for the players. The sellers are non-strategic in the in the game. They are not. We don't consider their strategies. So given this, for each edge, for each seller, what we just calculate is the bid that will give the seller the maximum payoff if they do a Pareto efficient exchange to give the bid to the buyer who bids it, right? So in this case, we have an equality subgraph of the initial social network, along which we see that each seller has the maximum. Each seller has the edge with the buyer with whom he can actually get a maximum exchange. Each buyer has the bid that he or she asked for, right? So in this subgraph, equality subgraph, what we do is we want to find a maximum matching. We obtain a maximum matching. We can use augmentation path algorithm to do that, and when we get a maximum matching, then we match up pairs, and only people who are present in all possible maximum matchings in this equality subgraph will get a positive payoff equal to the bid they said. All the other people will not all the other buyers will get a 0 payoff. So we have another work in which we showed that there exists a stable matching in this case, which is the generalized stable matching problem, and through which we show that there exists a Nash equilibrium in this fictitious game. Right? So the existence of a Nash equilibrium in this fictitious game once is proved, then we create a stable strategy profile, pairwise stable strategy profile from the Nash equilibrium in this fictitious game. So how do we do that? Pick any Nash equilibrium in the fictitious game. We know that the buyers who are unmatched in this exchange network induced by that strategy profile will have the maximum utility they can derive will be 0, right? So, so if that is 0, then we don't need to care for the unmatched buyers. So let's only focus on the matched buyers, the buyers who are matched. So now we can design a strategy profile in the original game. For each buyer who is matched, pick a seller whom he is matched to, and a Pareto efficient term of exchange that will give the buyer the bid he proposed or the utility he is making. So we know that exists because that's how the game was designed. So for this and for the sellers, we also do the same thing. So now we have defined strategy for the buyers and the sellers who are matched. For all the unmatched buyers, we don't care for because they will always get a utility of 0 in this game. So for them, we can arbitrarily pick any seller and say, and the terms of exchange could be 0, 0, and it will still be good. So this is a stable strategy profile. So we show this by saying that if it is not a stable strategy profile, then it won't be a Nash equilibrium in the fictitious game itself, right? So that is one of the key results. So if you have any questions, I'll take a 2-minute break. You should ask because that was an important result. Otherwise, I will go ahead with the next one. Okay, so let's move further. So now when we showed that the stable exchange networks exist when they are socially efficient. So technically, they're under a very limited set of utility functions in which you will see that these stable exchange networks are also socially efficient. The first one is a linear utility function. So this is in the matching markets, or some of the literature in sociology, like Emerson Cook, people have done experiments and shown that this is the case. And also in Kleinberg-Tardo's work, you will see similar results coming out. So when the utilities are linear, then it's pretty much boils down to a splitting of a pie. Similarly, when the utilities have a quasi-linear form with the same numerator, or example, when the money is involved. So money is kind of a normalizing thing. So apparently, if you can say that utilities are same as money, then you can give money to people, and then if they have transfers between people, then you can have a efficient strategy profile which is also stable. Thirdly, when the preferences are homothetic. So we will come to let's first see the what happens in the linear utilities, and then we will show that the homothetic utilities can also boil down to the similar scenarios. Okay. So what happens in the linear utilities case? So suppose the exchange the exchange is like giving mi units of good 1 and asking for mj units of good 2, like rice or wheat, rice and wood, for example, right? So in any exchange between I and j, I derives viy, which is the marginal utility of good y, minus vix into x, which vix is the marginal utility of good x. So the amount of good he gets, the marginal utility of times the marginal utility of the good x, which is the wood, and then minus the amount of rice he gives in times the marginal utility of rice. So that is the utility that actor I derives in this exchange, right? So this is if we see this graph, along this line is the rice and along this line is the wood, and for actor I we see that this line is the line along which the utility of the individual does not change, stays 0. Like if he is indifferent to not exchanging anything or exchanging any point along this line, right? And this is the same thing is this thing for the other actor or the woodcutter, right? And so as you move up this line, for example, you move along this line, then the utility of the farmer increases, right? And similarly along this line, the utility of the woodcutter increases. So the set of possible, rationally possible exchanges between these two guys will be in this region, right?
That line is the constraint?
Yes, and this line is the constraint. So it could be all this reason, but if you put this constraint, then you are limiting it, right? So all the Pareto efficient exchanges will occur along this line. So for example, this point is a Pareto efficient exchange. The important thing is that when we have these linear utilities, then the thing is that okay, if the farmer says that I have infinite amount of utility for both rice and for both wheat, then in an efficient scenario, you will give everything to that farmer, and the woodcutter won't get anything. So we need to change this thing. We need to do some normalization of the utilities. So we normalize the marginal utilities. They said, hey, you can't just keep on bidding, saying very high things about your utilities and get everything for yourself. You have to compare. You have to the utilities have to be comparable. So you said, okay, the sum total of your utilities, marginal utilities for rice and wheat is say constant, for example, right? So you normalize it. So you normalize the marginal utilities by dividing it with the total, the sum of marginal utilities of the rice and wood, right? So when we do that, then we see that along this line, the sum of normalized utilities for the farmer and the woodcutter is the same. So what it turns out to, that it means that in this social relationship, the sum of normalized utilities for these individuals is maximum normalized in these individuals is same. So they can just split that amount among themselves, and they can also find an exchange that will be compatible with that, right? So the bargaining happens along this line in this case, right? So this is what is happening in the linear case. So that's how it boils down to the bargaining problem in social networks. And so as I said, then in that case, the pairwise stability solution is just like this. So in that case, the pairwise stability condition is that two edges who are not in an exchange relationship or in a matching, for them the sum of normalized utilities will be higher than the surplus they can actually get in that relationship, which was along the constraint line, right? And whenever they are in a relationship, this sum of the marginal utilities they are deriving will be equal to the value of that exchange relationship along the contract line, right? So now when we see this thing, this reduces to a weighted matching problem. We have the stability problem initially that I proposed. Here Vi is, instead of showing the whole equation, I just said Vi is the normalized utility of individual. So stability problem is to minimize the Vi such that the constraints exist. No two people not in a relationship are deriving payoffs that such that the sum of payoffs is less than the possible social surplus between that exchange, and all these Vi should be 0 so that they're individually rational, right? The efficiency problem, on the other hand, is to find out the matching, the maximum weighted matching, and the weights are the surpluses involved in each exchange relationship, right? So given the constraint that each person can be matched to only one person, or a person cannot be matched at all. So this is the integer constraint, right? So this is actually an integer programming problem. So technically what happens is that you can remove this. You can remove this, and the solution that will come out of this problem will actually be an integer solution. So that's why we have this thing. So what happens is that this problem is a dual of that problem. So you can solve either of them, and you get the result. So the stability problem and the efficiency problems are duals of each other, and the solutions of the stability problem is the same as the solution of the efficiency problem. right? Corresponds to the solution of the efficiency problem. So that way you see that stable networks are also efficient networks, right? So why is it also true for homothetic preferences? Linear preferences I understand, but general class of homothetic preferences, why it happens? So homothetic preferences we can reduce it to just homogeneous preferences, and say the homogeneous preferences say that if there is a bundle A and a bundle B, and the utility of bundle A is same as bundle B, then if there exists another bundles 2A and 2B, then the utility of bundles 2A and 2B will also be the same, right? So if we have this constraint, right, then we see that then we can actually normalize the utility functions again and obtain similar results, that the sum total of normalized utilities along any edge is same for all Pareto efficient exchanges along that edge. Here we don't need the capacity constraint on the edges that we had in the linear case, right? So that's why the homothetic preferences are very similar to linear preferences when it comes to the stability and efficiency, and we can have the same duality of the stability and efficiency, and we can get the result, right? So that was the debate. Yes.
Can you comment on how truthful these agents are on this network, and does stability and efficiency properties translate when you have agents lying each other boundary?
Yes. So we have not studied we are not talking about the mechanisms here. So technically, when you have the mechanism, then we would see what if truth telling is an incentive compatible behavior. Here we are just doing equilibrium analysis, and so saying truth or not is not one of the strategies here. That is actually another line of work, that okay, if you design this, do there exist lying agents that can actually get there? Turns out in the myopic sense, they will not. If they are myopic and they can lie, they will not do any better by lying about this thing. Right? But that is another line of work when you design mechanisms for these markets, right? Okay. So now, what natural myopic behavior can lead a society to a stable exchange network, right? So that is an important question, right? So we consider this myopic behavior, right? So this dynamics is that at every time instant you pick one farmer, right, and ask him to pick a woodcutter and pick the exchange terms of exchange that he wants to have with the woodcutter. How much rice to give, how much wood to take, right? And if you do that, then if a farmer does that, then the woodcutter gets an option to respond by saying yes or no. If a woodcutter says no, that trade does not work, and you go pick another buyer. If they work, then they both get into a contract. So this is a contract which says that in all subsequent time steps, they will perform an exchange. Right? They can break the contract later, but yes, for now they will perform an exchange. Right? So this selection process could be random, as long as you have certain constraints. It's not that you're not going to pick anyone. Everyone gets chance at some point of time, right? Okay. So the other thing is that if someone changes a partner, or breaks the contract, he or she gets charged a one-time contract breaking fee, which could be anything greater than 0, right? So that is the case. So here we see that two people change their strategy simultaneously in any round, and all the other people have the same strategy, right? So you want to see if these dynamics converges. So first important lemma about this dynamics, the three key observations that are critical for the dynamics to converge. They are monotonicity conditions. So the first thing that the dynamics shows is that for any woodcutter or a seller, the normalized surplus does not decrease. It either stays constant or it increases in the time step. The reason for this is that like if I am getting a lower offer, I will never say yes, and so I will never reduce my utility, right? Okay. So secondly, the thing is that if there exists a buyer or a farmer who does not have any of her neighboring woodcutters to such that he can persuade the woodcutter to by giving him a better offer to get an exchange relation with that woodcutter, then any further time step she will not be able to do that, or he will not be able to do that. So suppose what it means that if a farmer is poor, he will always remain poor. That is the poorest thing about the farmer. Okay. And third thing is the farmers, they never break a contract once they are made. The ones to break the contracts are the woodcutters. So the reason is that the farmer makes the best contract in the first place, and if he could have gotten something better, he would have done in the first place. So that's why they never break a contract, and all the contracts are broken by the woodcutters, right? So that lemma is very important to prove this first theorem, which says that if this selection is done only for the buyers or the farmers, so every time you select an actor in this network, you only select a buyer or a farmer, then and also the selection function has this constraint that if I select a buyer and buyer proposes a contract to a seller who agrees for the contract such that the seller was in a relationship and that contract is broken, then the buyer who lost the contract will get an opportunity to propose the next time. If we have this constraint on the dynamics, right, and also the probability of selecting any buyer is greater than 0 for all the times, right. Okay, if you have this constraint, then if you start from an empty exchange network, then it will converge almost surely to a stable exchange network. So almost sure convergence is important because we have to show that just to show this thing you can use the Borel-Cantelli lemma to show that the set over which it will not converge has a probability 0. Okay, so this is an important result, and so what we said that okay, if it was only buyers and we had this constraint, turns out it is not that constraint is not that important. Even if we do not have this constraint that if a buyer loses his contract, he gets a petty chance to propose a contract to some other seller, it still converges almost surely, right? And the third result is that okay, what we are doing, we are actually just generalizing it, right? Take a constraint, relax this constraint, and see what happens, and then see what happens. Thirdly, the result is that if we don't just select buyers, we select sellers also, then also it will almost surely converge to a stable strategy profile. And it's mainly so what happens when we have like both buyers and sellers coming. Let me show you an example here, right? So we have these two are the buyers and these two are the sellers, right? And so the sum of normalized surpluses on these edges is 1 each, right? So if one gets a chance in the first time, everything is 0. There is no exchange network right now. If one gets a chance, he will propose to get all of the surplus in this and give 2 0, right? So give 3 a 0. So what happens in 3 chooses? Next time you pick 3, by example, right? So then 3 says, okay, no, I will not get it. He'll break this relationship. He will give 0 to 2 and get 1, right? And then third time step, you pick 2. 2 will break this. 2 will form a relationship with this. Fourth time, you give chance to 4. 4 will break this relationship and form a relationship with 1. And this cycle will keep going on and will never converge, right? But the almost sure convergence says that okay, there exists some cases where it will not happen, and that's why you have almost sure convergence result. Right. Okay. So that was okay convergence. So what in the first place when we say that okay, if you only select buyers, that result is the payoff that it will give is actually buyer optimal. What it says that when it converges it to a point where the buyers will make payoff such that no other possible stable exchange network will be the case in which buyers are making more payoff, right? So there does not exist another strategy profiles which is also stable and buyers are making payoff. And this is not the sum total of payoff for the buyers. It's individually, each buyer will be making a higher payoff than they can make in any other possible stable strategy profile. Right? So that's why it's a buyer optimal. If we, instead of choosing buyers, you choose sellers, it will be seller optimal. And in the mixed case, when you are choosing everyone, then it will converge to one of those things, either buyer optimal or seller optimal. Okay, so that was all about the theoretical results. Now see, okay, we did lots of theory, but we want to see what do people do. Do people do any of these things? So let me quickly show you some of the experiments we did. This is we did experiments in collaboration with Kobe Gal, who was at Harvard and now is at Ben Gurion University in Israel, and Iyad Rahwan, who is visiting MIT right now. So we brought people into the lab and put exogenous networks around them. So I'm showing you two networks over there, and all these networks are bipartite networks. And the person was in a network at a position in the network. They didn't know where they were. They didn't have the visibility of the whole network. They only could see their neighbors through the game. And they were playing an online game. So the game board looks like this, right? So this is you. If you are a user, this is you, and these are your two neighbors possibility. Consider this example. Each person has two neighbors, right? So each person is given one kind of chip, which you can map it to rice or wood. So for example, me gets 2 red chip, and plus and star get 3 purple chips each. This is just one example. Now the yellow thing is actually a currency in this game, which is not used explicitly for transfers, but how their utility is mapped, right? So we want to have a utility function given to people instead of doing it. So the number of yellow chips they end up with will be proportional to the amount of money they will receive for playing this game, right? So the goal of the people is to gather as many yellow chips as possible, right? The constraint is that each person can trade with only one other person in this game, right? So the value of red chips is less to me as compared to the purple chips, right? So this me may get exactly 1 yellow chip for 1 red chip, but he may get 3 yellow chips for 1 purple chip. So the me wants to exchange red chips for purple chips, right? So this is the idea. And plus and star on the other hand have the other way. They want to get more red chips, and they can get away with give away the purple chips, right? So this is a thing going on. So how do people do trade? So
there are different payoffs for the red and the purple chips for different people.
Yes. So each person has a defined value for red and purple chips.
And is it visible to like for me, like what are the value functions for different people, or just I just know my?
No, you just know your utilities. The thing is that you also there is some information given to people about their neighbors, which I will come to after I show this. Is how much per yellow chip they are making in their game in the game at present moment, right? So these are myopic dynamics we are trying to see, right? So we see that each person sees that, okay, what is the value that all her neighbors derives in this game, and then he picks or she picks her strategy, right? So how do they do it? So at any time instant you pick one buyer, and that buyer gets an opportunity to propose a trade, right? So this buyer says that so he proposes a partner here. So here, for example, he proposed plus, and he can choose to send chips. If he has purple chips, he can send purple chips, but if he has red chips, he can send red chips. He can send red chips and ask for purple chips. So at the side, you see what is the result, how much yellow chip you will end up with, and how much yellow chips the other person will end up with, right, if this trade goes on. At the same time, you see current, which shows how much yellow chips you are receiving right now if you do not go on with this trade, and how much yellow chips the other person is receiving right now if she does not go on with this trade. So it talks about the outside options, what you have over here, right? So in this case, and we also have this information available for all the other partners that are there, whom you are not proposing a trade to. So then you can decide, okay, no, this is not happening, maybe I should go somewhere else, right? So this is all the assistance, a lot of assistance being given to the users to make decisions. Turns out it is, with some people, even then it is a little hard for them to make decisions.
So let me understand. So in your graph, the graph is always fixed, it's never changing.
Yes, thank you. That's a good question. So yes, so for the purpose of each game, the graph stays same. So the social network does not change. What changes is the exchange network, which is a subset of the social network along which the exchanges happen. When people change partners, the exchange network changes. Right.
So in the first case, like the node 2 can only trade with 6 and 7, but no one else.
Yes. So node 2 can trade with either 6 or 7, but no one else. No one else. Yes. Yes.
What are the phases of the game? So I propose something, I wait until everybody proposes, and then
No.
accept.
So this is not a simultaneous bidding. This is not a simultaneous bidding. So here one person proposes, and whoever she proposed to responds by agreeing or disagreeing, and if they agree, there is a contract formed between them, and then the next person is chosen to propose.
Okay, so for example, I'm number 2. When I'm proposing, number 1 is not proposing anything to number 6.
No, but if number 1 could also always already be in a contract with number 6, that's okay. And
can I see that?
You can see, you cannot see whom number 6 is in a contract with. Number 2 only sees what is the value that number 6 is deriving in this game right now, or whether she is making a trade or not, you don't know, but you see how much she is making right now.
So I'm number 2, and number 6 is in a trade with number 1, and I'm making a proposal to number 6. So
Yes.
at that point, number 6 can either break the relationship with number 1 and start trading with me, or
Yes.
stay put.
Yes.
And if number 6 rejects it, I'm not making an exchange.
No, you're not making exchange.
I can propose to 7 again because I'm rejected.
You are rejected. So you can propose again when you get a chance again, not in this round. Yes. So you have, when the round starts, actually you have to make a two-stage optimization. First, choose which partner to choose, and then choose how much to give. So you want to choose a partner with whom you can get the maximum benefit, but you want to make sure that the partner gets at least as much how much she is making right now. The partner will say no, right? So if you say it in a two-stage game scenario, the first thing is, in the first stage is I choose which partner to choose and how much to give, and the second stage is the partner's strategy, whether he wants to accept or reject. Right? It's a kind of an ultimatum game, right, that you are giving. Okay, so this is the experiment, right? So what I'll just show you the key results that we come out with experiments, right? So 3 important results, and then we have some other behavioral results that we will show. So first thing, yes, the dynamics converged. Even with a network with a large diameter like the 10 people network, the dynamic, the tin paper line network, the dynamic converged in 28 iterations. So the total number of 28 proposals. So you have also the opportunity to skip the proposal. Sorry, I didn't say that. If you think that you cannot do anything, you can just skip the proposal. So the dynamic converge. When we say the dynamic converge, it means that people just skipping proposals. Everyone skipped proposals. They said, excuse me, they decided not to break any relationship or not to propose any trade because they probably thought they can't do any better. So they were doing the best, right? So that's when we say that that's the dynamics converged, right? So yes, the dynamics converged, and the dynamics converged to epsilon stable strategy profile. Sorry, when I said in myopic dynamics that you can break a contract by giving giving a contract breaking fee, one-time contract breaking fee of epsilon, which is greater than 0. So here it was 1 yellow chip, right? So every time you break a contract, you have to give away 1 yellow chip. This is important in the sense of not always all the time running the experiment, but theoretically it is important. why it is important is that if there are 3 people or 4 people in that scenario, what happens is that the seller who is, if there are 2 people fighting for one seller, 2 buyers fighting for one seller, and the seller is getting 0 in the first case, then the other buyer can also propose the same trade to the seller and seller will say no. Right? But with the contract breaking fee, then you have this thing that you have to propose a little higher value to the seller so the seller will accept. Right? Otherwise this is a very peculiar scenario, we don't, and it has some natural implications too in the real life. Right? You are in a committed trade relationship, you don't want to break anything unless you are getting at least something better, not if you are getting the same value, why will you do that? Right? So that epsilon stability is important. So epsilon stability says that it's not stable, but it's not very far from stable either. Right? It's not very far from stability either. So that's why it converges to a epsilon stable exchange network. Right? Now, so as I said, it was not stable, but it was always epsilon stable. Right? And there's also the notion as the discrete nature of this experiment. You cannot give like half a yellow profile or keep reducing it to 0. So in a limiting case, you can say that okay, epsilon stable will actually be the stable profile. Right? Okay. Now important things about the behavior. Right? So did people behave rationally? Almost all the time, but there were some cases which is very funny, and in some cases it was difficult to see that people did understand that it was a myopic thing. Like some people looked forward. They said, okay, if I am getting an offer from this guy and I am not doing much better, but that guy is doing a lot better, then let me hold on to this so that guy will come back to me. This was not a myopic behavior, this is a far-sighted behavior, which maybe some people did not get it. The other things that people did was they didn't want to be exploited. They said, okay, if that guy is getting a lot and I am not getting too much, I am not going to accept it. Right? So even though they were better off than what they are right now, they did not accept it. So they didn't want to be exploited. Third thing is that people are often fair. Right? Sometimes sometimes they're fair. So they don't want to exploit other people too. They want to have some fairness in the exchange relationship. So technically you can theoretically show, and one of our results that we're not showing here shows that a fair strategy profile is also the most stable one. In the sense it is proof to the coalitional deviation. Suppose all buyers come together and all sellers come together and then they want to exploit each other, then the fair strategy profile will be one in which these coalitions will be pretty useless. Right? So there are things. So why are people fair? So that's another interesting question that you can take from here and investigate. And maybe for further experiments will also help us identify why are people fair. Another thing is as the game progressed, people started becoming more exploitative than when they were before. So one possible reason that I can think of is that they learned more about their position in the game. They think okay, they can get more, and then they started getting there because they know that okay, if the game ends right now and I'm not getting anything, then I will make 0. But if I am fair, at least that guy will accept, and then I will make something. So they will have a positive payoff. So that's what people were doing initially. And as time progressed, they said, okay, no, I can get more, and they moved towards it, and then that's why they became more exploitative. What about the final exchange network, right? So if you see that, for example, the linear case, what happens is that the set of payoffs that people can derive, for example, for 2 people, it could be anything between here and here, as you saw in the Pareto efficient line, right? But the fair trade will be somewhere here in the middle, right? So, but in the buyer optimal exchange, suppose this is the buyer, right, and this is the seller. It should always exist here, so the 2 does not get anything and 1 gets all of it, right? So But this fair outcome is actually a unique outcome, right? So what happened was it was not here, it was somewhere here or somewhere here, but it was not fair, not totally exploitative. In a polytope sense, suppose this is one particular polytope that you see, multidimensional and projecting into 2 dimension. Suppose this is the line along which you will have all the exploitative outcomes, bioptimal outcomes, right? It could be one of these lines, or could be all the whole line. And the fair outcome will be somewhere here. But the result was almost all the time in the interior of this polytope, but not at the point where the fairness was not totally exploited. So this is one thing that we observed in this experiment. So these were the key experimental observations. For future, what we want to see, definitely the applications are in mechanism design, and we want to explore that. But from the perspective of this line of work, we want to see what do far-sighted actors do, right? So we had some notions coming out of the experiment that people act like that, but what do they do in general? And when they have some uncertainty, like their uncertainty, like whether you will get a better offer or not, or then what would you do? Are long-term relationships preferred? Like, do people do these come into these committed relationships, right? So these are some things that we want to see. We expect that we will form long-term relationships immediately in a fair manner, but that depends upon the amount of information they have, or if there's some learning going on, then there will be different things, right? Okay. Now what we saw today was kind of a partial equilibrium analysis, which says that, like a farmer and a woodcutter, right? But of course there are other things like boatmen or butchers or everyone, right, in the economy. And I need to get lots of different things. So what you saw today is a farmer or woodcutter. There also could be a farmer and a butcher social network, right? So all these social networks are layered. So all these things can be analyzed in this mechanism. What we did not see was substitution effects, right? So I have enough rice to get this much amount of wood, and I can also get instead of wood I can also get some meat, right? So what you may like to do is to get a combination of wood and meat, right? You can substitute some wood for meat or meat for wood. There the analysis becomes much more richer. And we want to study that. Like, what are the substitution effects people are having? How does this affect the social relationships or the exchange relationships that they're having, right? And because that is a much richer set of problems that will come out of this, and it would be good to study. Okay? Thirdly, suppose these are all not just consumable goods. These goods can actually flow. For example, information is one example, right? Information is one example to the sense that when it flows, it does not disappear from where it went from. But there could be other things like a bicycle that is shared among people, or I keep giving to other people and getting more, right? So those goods do not lose their value or do not lose their value to zero as it is passed to other people. It's not like consumer goods. It's so what happens in those cases? So when the supply or the presence of goods changes in the market as it flows, how does the market react to it, or the social network react to it? What happens in this scenario? That is another interesting line of work that comes out of this thing. So that was my presentation. Thank you very much. It was a pleasure coming here and giving a talk to you, and I'm ready for questions.
We have some minutes for questions, discussion.
Yes.
So your model kind of assumes that you know the network structure, and then you know the utility functions that come with the network structure. It seems like in the human experiments, people spend like 28 rounds to discover the network structure and then discover the utility functions of those people so that they can understand which are acceptable or not.
So technically, people do not discover the network structure or the utility function of other individuals. They only discover their worth in this network, that how much they can derive in this network, or how much their neighbors will give to them. So they don't have the complete information. They will never get the complete information of what the complete network looks like. There are infinite possibilities what the network could look like. Well, technically in a finite network, not infinite network, not infinite possibilities, but yes, but a very large number of possibilities do exist. So they don't know that.
But in a real world situation, you would have this network structure changing,
yes.
new people coming in, they get out, and also utility functions also change, so that once, like if I collaborate with you or do an exchange with you this round, this exchange may not be beneficial for me 3 rounds from now, because maybe if I'm a farmer, it changed, something changed with the
True.
So how do you think this convergence will change with respect to these changing situations?
Yes. The very important questions actually, and the non-stationarity in the networks is very natural, and that is something that we definitely have to look into. From my thing, what will happen is that instead of the whole general equilibrium literature is actually a equilibrium analysis, a stationary analysis, and we have to start looking for sub-game perfect equilibriums, because when you're talking about this non-stationary, there is also uncertainty that I said. We don't know how the networks will change. We don't know what is going to happen. Then what you are talking about is sub-game perfect equilibrium. It could be ex ante. You have certain assumptions, certain belief of how the network, the world will change. The world is non-stationary, but we have certain faith or certain belief in how it is going to change. It's not totally the world today says something about the world tomorrow. It's not totally random. So the things will change in a sense that we will have a dynamic equilibrium, but yes, there will be possibilities there. And it's a very interesting line of work to do.
So I was thinking of, have you done analysis with respect to graph structures? So to give you an example, right, you mentioned about a farmer in Nicaragua not talking to one in, say, Zambia. But now with the internet age, right, that's going to change. It's going to change the structure of the graphs, right? You get more connected.
So yes, but the thing is that different kind of exchanges will happen along different kinds of graphs, right? It is easier to change information for a farmer in Nicaragua to a woodcutter in Zambia, but you would probably not exchange 1 bag of rice for 1 cart of wood, right? So the different types of goods will have different properties. That's true, and it may be interesting to see if you have networks which are becoming small by creating these long links between people who are like very far apart, making a small world, or what happens. Yeah, it will be more interesting to study this when the goods can actually flow, and they are not totally consumable goods, right? Yes.
So I would speculate that in the linear case, for example, the most exploited sellers are on the edges, right?
Yes.
The ones that have no other options, and then along time the buyers discover that these sellers actually have no options, and though they should offer to them something that isn't fair, right?
That's true. What happens also depends upon the capacity constraints of the edges, and also of the initial endowments that people have. So unavailability of a partner makes you prone to being exploited, right? Makes you that. But it also depends upon what partners you have. So the people on the edges in a network where there is homogeneous will definitely be exploited, right? But it's not to say that people inside the network are like very powerful, right? So it turns out that people, in some cases, people inside the network can also be very weak. And they may have lots of links, but they may not have much endowment, or they may not have much trading capacity with those links, so they cannot do that. Also, the example is that, okay, like if you have a beggar who is...
That's maybe an artificial constraint from the fact that that the buyer working with you can, if he's selling to you, can only sell to you. Because if he were able to sell to you and to buy from you and also from someone else, then he would use you and also not lose from that, right?
Yes. So here's why this happens. Suppose consider a simple example of me selling my rice for money, right? I'm selling to you and selling to Ashish. I have an option to sell to you and Ashish. If you are giving me a higher price, I will never sell to Ashish. I will sell all my rice to you. So it's not as unnatural as it seems, and it's also very common in when you have
a higher price, but I'm only willing to buy a very small amount.
Yes.
Then you don't want to work with me if that excludes Ashish, but you do want to work with me if it doesn't.
Yes. So when you have multiple exchanges, yes, that becomes a much richer scenario. So what happens in multiple exchanges is that what we will see is that in a lot of graphs, the marginal returns for all the players for any changes in this set of exchanges will always be the same. So let me draw an indifference curve. How does it look like in real life scenario? So if you see this, so an indifference curve is a curve. Like suppose this is a mi and mj, right? So this is the exchange. Like I'm giving mi and getting exchange. In return, I'm getting mj amount of good, and this is my exchange curve u1 equal to c, and this is exchange curve for the other guy u2. Sorry, indifference curve for the other guy u2 equal to p for not p is complicated. C1 and C2, right? Then along this indifference line, I'm getting C1 utility all the time. In this case, so what it says is that the tangent here is same for both these cases, and this is the point. So if this is one thing, and you have multiple exchanges, a stable thing will happen at a point where all these tangents are the same, right? So if I'm exchanging with this guy, the other guy I'm exchanging, the tangent, it should be the same at that point. So you will see results like that. It often becomes very similar to the market scenario, and in a limiting cases, when you also have the flow of goods, it becomes very much like markets. But the transients are something that are more important.
All right. Thank you.
Thank you.